Assalamualaikum warahmatullahi wabarakatuh. Today we will be presenting on drone communication system and their role in next generation in aerospace network. Drone communications refers to the exchange of data between an unmanned aerial vehicle or UAV and external network nodes such as ground control stations, satellites, and cellular networks. The communication system operates through two main links: the uplink, which sends command and control instructions to the drone, and the downlink, which transmits telemetry information and sensor data back to the operator. With the development of 6G technology, drone communication is evolving toward terahertz-based networks and space-air-ground integrated networks, enabling faster, smarter, and more reliable connectivity. Drone communications offer several advantages compared to conventional terrestrial communication systems. One key advantage is line-of-sight connectivity. Because drones operate at higher altitude, they can establish clearer communication paths with fewer obstacles blocking the signal. Another advantage is rapid deployment. Drones can quickly provide communication coverage in areas affected by disasters, emergencies, or network failures. Drone networks are also highly flexible depending on the mission's requirement. They can operate using power-to-point, star, or mesh network topologies. In addition, modern drones are equipped with onboard processors that support edge computing, allowing data to be processed locally and reducing communication delays. This slide shows how communication is established between a drone and the ground station. The process starts at the data source, where information is generated by the drone's flight controller and onboard sensors. This includes telemetry data such as GPS locations, altitude, speed, and battery status, as well as payload data from cameras or other sensitive devices. The generated data is then processed by the transmitter. During this stage, the information is encoded and modulated using wireless communication techniques such as OFDM before being converted into radio frequency signals. These signals travel through the wireless channel, which can be either an air-to-ground or air-to-air link. While propagating through the environment, the signal may experience path loss, interference, and fading caused by the obstacle, weather conditions, or movement of the drone. At the receiving side, the receiver captures the signals and performs demodulations and decoding to recover the original information. The recovered data is then sent to the ground control station for monitoring or the drone's flight controller for command execution. This continuous communication loop enables real-time command transmissions, telemetry monitoring, and payload delivery, ensuring safe and reliable drone operation. Drone communication systems are widely used across many industries today. In delivery services, communication links enable drones to receive navigation instructions and transmit real-time location updates during package transportation. For civilians and monitoring, drones provide live video feeds for border security, traffic management, and infrastructure inspection. In disaster response operations, drones can function as temporary airborne communication platforms, restoring connectivity when ground networks are damaged. In smart city environments, drones communicate with IoT devices and control centers to support environmental monitoring, traffic analysis, and public safety applications. These examples demonstrate how reliable drone communication is essential for enabling efficient and intelligent UAV operations.
There are four main things during drone communication. First, interference. When other drones, Wi-Fi routers, or even microwave oven use the same frequency, the signals collide and the drone can hear clearly. Second, blockage. Concrete buildings, trees, or hills physically stop the signal, or though when the drone flies behind them, the connection breaks. Third, attenuation. The signal naturally gets weaker as the drone flies farther away, like whisper fading over distance. Fourth, weather. Rain, fog, and snow can absorb or scatter the radio wave, reducing range and reliability. Now here is how this problem affects performance. With no interference, latency is only 20 milliseconds. The drone can operate up to 5 km, but with interference, latency jumps to 400 milliseconds, a half-second delay, which a flying speed means the drone travels several meters before hearing a command. Packet loss hits 25%, so 1 out of 4 command or video packet never arrive. Effective range dropped to only 1.2 km. Let me give you a real example. A medical delivery drone is carrying anti-venom in heavy rain. It must pass behind concrete hospital building. Rain causes attenuation, absorbing 15 decibel of signal power. Then, the building creates a complete blockage for 2 seconds. Packet loss spiked to 80%. The video feed freezes, so the operator is blind. A corrected command tells the drone to drift instead of over, and it drifts into a tree. The fuel system triggers, the drone returns home. The anti-venom arrives 45 minutes late, putting the patient at risk. Well, this is why noise is not just annoying, it can cause mission failure, crashes, and delays.
Good day to our lecturer and fellow classmates. I will be concluding our team presentation by exploring the horizon of drone communication, specifically focusing on 6G network and quantum technologies here on slide 9. As drones become more autonomous, they face highly sophisticated AI-driven cyber threats. To counter this, we introduce the quantum secure interference. By utilizing the quantum cryptography, we ensure that the communication link between the drone and the controller is mathematically impossible to hack or jam. Furthermore, to combat the environmental noise and the blockages that my friend mentioned, we utilize AI-driven mitigation and quantum error correction (QEC). This allows the drone to dynamically detect the interference in the real time and automatically correct data errors before the connection drops. Moving on slide 10, how does 6G change the game? 6G introduced an integrated space air-ground network. If a drone line of sight is blocked by a massive skyscraper, the network instantly reroutes the signal via low Earth orbit satellite with an ultra-low latency of under 0.1 millisecond. This breakthrough unlocked the safety requirement for a massive future application such as the fully autonomous flying taxis and large-scale emergency rescue operations. To conclude on slide 11, mastering drone communication requires us to look at the entire life cycle, understanding the core system components, analyzing how noise degrades performance, and deploying future-proof quantum and 6G technologies. By merging these three domains, we can build a drone ecosystem that is fast, robust, and also can completely secure. Thank you for your time. So that's all from us.